When the James Webb Space Telescope finally measured the expansion of the universe, we knew we had a problem. Webb was able to pinpoint the distances to distant galaxies with unprecedented clarity, helping us to gauge how fast the cosmos is stretching apart right now. But what we saw was not the smooth, predictable growth that our models of the universe had promised, where the expansion rate aligns neatly with the echoes of the Big Bang. The modern universe was racing ahead. It was expanding too quickly. The numbers didn't match, and the discrepancies we started to uncover in the data had grown too stark, too insistent. Some began to whisper that our foundational theories were flawed, and cosmology was fracturing at its core. And while some of those tensions have eased as sharper observations poured in, other riddles only deepened, casting shadows over everything we thought we knew. But in a bizarre revelation, one of the most enduring enigmas in all of this might be on the verge of cracking open thanks to an anomaly lurking in our cosmic neighborhood. It's called the Coma Cluster Void, and we've just seen it warping the fabric of space-time in ways that defy expectation. And it might just rewrite the story of reality itself. A universe takes eons to unfold. Primordial fluctuations in the quantum foam need time to swell under gravity's pull, until vast structures emerge from the void and galaxies ignite in the darkness. These galaxies drift apart, and from their motion we derive the Hubble constant, the heartbeat of cosmic expansion. Cosmologists have peered into the depths of space and, based on what they've witnessed, forged models for how swiftly the universe should be growing and how its fate might play out, which is why the JWST data ignited such turmoil. The expansion was not as the equations foretold. Fortunately, some of those early alarms proved resolvable in the years after the telescope's launch. For instance, the brightness of distant supernovae we could trace through Webb. This luminosity suggested that the universe's sprint was far too brisk, demanding revisions that should have taken billions of years longer to manifest. And yet, there it was, a relentless surge at the edge of our vision. However, researchers at institutions around the globe, scrutinizing Webb's vast surveys, realized there could be another layer to this excess velocity. And paradoxically, that layer was hidden in the very measurements themselves. If we assume that subtle, systematic errors had crept into earlier telescopes' views, distorting the light from ancient stars, then the fierce precision of Webb's infrared gaze could strip away those illusions, revealing a truer pace. This explains why the expansion seemed so accelerated and was skewing our calculations. Once you correct for these veiled biases, the rate steadies, and harmony returns to the cosmological framework. Problem averted. That underscored how vital precision is to unraveling the universe's tempo, which was, in itself, a quandary, because the Hubble constant itself shattered our predictions too. In particular, cosmologists grappled with the vexing puzzle of why it diverged so sharply. For local measurements, drawn from nearby galaxies and their explosive beacons, there was no issue. These yield a Hubble constant around 73 kilometers per second per megaparsec, and we grasp well how they arise. They stem from the recessional velocities of stars we can almost touch, and there has been ample time for such data to accumulate in the observable cosmos. But scientists were floundering with the cosmic microwave background readings etched from the universe's infancy, implying a slower expansion of just 67 kilometers per second per megaparsec, which anchors the vast architecture of dark matter and energy at the heart of galaxies. And due to something called the Hubble tension, there just shouldn't be such a rift between the near and the far, the now and the then, and yet there it was, and it was widening. Local probes can refine as observations sharpen, provided you calibrate the cosmic distance ladder meticulously, but how drastically? In the early 20th century, an astronomer named Edwin Hubble formulated the notion that the universe's stretch was uniform, a constant woven into space-time's weave. This is what drives the reed shifting of light from distant realms. A faint stretch, yes, but enough to reveal the drift. This is what propels galaxies on their eternal flight. That subtle momentum, imprinted by expansion. For the rate to hold steady, it must balance against the gravitational tug of matter, seen and unseen. And at a certain threshold of discrepancy, not even our standard model can bridge the gap. This is called the Hubble tension, and universes that teeter on its edge, such as ours, with measurements clashing by nearly 10%, are just a whisper away from demanding revolutionary physics. For the cosmic microwave background, you might think this would be straightforward. Isn't the CMB the pristine relic of the Big Bang, untainted by later chaos? But the interpretations are a different tale. As we discussed, the Planck satellite mapped this afterglow with exquisite detail, yielding a slower Hubble constant that dovetails with lambda cold, dark matter, our bedrock paradigm. With discord comes the need for reconciliation, and the universe must adhere to a single truth. So even though, given enough scrutiny and data, local measurements could theoretically align with the ancient ones, it doesn't seem likely that this explains the chasm we observe. Simulations have been executed, and although it's conceivable to nudge the numbers into accord, it would require those early universe parameters to be finely tuned since the dawn of time, which just doesn't occur. Realities in flux often veer off course and need anomalies to realign. To compound the intrigue, we're not entirely certain that the local Hubble constant is the matured echo of the primordial one in the first place. Though it feels intuitive to presume so, scientists have been perplexed by the absence of transitional evidence in our cosmos. To be candid, they've uncovered scant traces, at least none beyond doubt. The CMB-derived rate is etched in the vastness, immutable, and there are myriad local probes affirming the faster pace in our vicinity based on the supernova we've charted. But bridging values are suspiciously scarce, with only fleeting hints. You would expect we'd detect far more. Desperate for clarity, scientists started to theorize that the Hubble tension arose from some other origin. Many cosmologists have delved into the possibility that because the universe's density varies on grand scales, we might inhabit a region that's underdense, a vast void skewing our local measurements outward. If this holds and emerging data bolsters the notion, then perhaps the expansion isn't uniform after all, even if such lopsidedness defies the homogeneity we assume in our expanded cosmos today. But this is far from assured. Data was beginning to hint that residing in a cosmic void might be the resolution the scientists sought. Then the coma cluster anomaly emerged, and the scales tipped once more. The coma cluster is a colossal assembly of galaxies, some 330 million light-years distant. It's so immense that its gravitational embrace warps the paths of light, bending reality around it. But even its vastness pales against the redshift we observe. The expansion has stretched its emissions into realms beyond visible, demanding instruments like Webb to pierce the veil. Yet the coma cluster's position was too close, 38 million light-years nearer than models decreed. It took the combined might of Hubble's legacy and Webb's resolve to confirm it at all. Even then, the cluster appears as a sprawling web of luminous threads. But the gravitational lensing from this web is telling. Distortions in the background galaxies reveal that our local bubble, this underdense void encompassing Earth, is inflating the apparent expansion in a manner no one anticipated. You see, the coma cluster crucially amplifies the Hubble tension, and not subtly, it's thrusting the discrepancy into our cosmic backyard. How is this feasible? It emerges that voids can indeed skew the Hubble constant, but only in localized bursts or through cunning geometries. For instance, primordial sound waves from the Big Bang can echo through the CMB, carving underdense regions. If all the density dips align in one expanse, the surrounding cosmos expands unchecked, while our void lags, mimicking a faster universal sprint from within. There are other avenues. While the tension posits that once the expansion rate climbs too high, all predictions unravel, there is a fleeting window before this where a void-riddled cosmos can surge into discord territory. Like a ravenous force, it might reap consequences later, but for an epoch, that acceleration transpires. If this rings true, it might just illuminate why the Hubble constants clash in our era. And assuredly, the coma cluster exists and is the starkest testament yet to a void-driven skew that compels our reckoning, much like the tension itself. It persists. It's now our duty to fathom how that's conceivable. So enigmas endure. If the coma cluster is ensnared in a void inflating our local Hubble constant, it affirms such distortions are viable. But what of the other peculiarities JWST unveiled? Where are the intermediate rates that should blend the ancient and modern on the path to unity? Why does the expansion spike in our vicinity more than equations permit? Do varying dark energy forms, ones that evolve over time, defying constancy, truly underpin this rift? Our models might be veering true, but a piece is absent or veiled. Voids exert a profound sway on our cosmos, and there are mysteries encircling them that space-time conceals fiercely. As formidable as JWST proves, it has not pierced this veil, not entirely, but perhaps we should temper our haste. Through our lenses, we have glimpsed the sprawl of infinities. That's an overwhelming torrent. Ingest too much revelation at once, and it might elude grasp. So whispers the tension, and its divide is never to be ignored. Except, of course, when the universe decrees otherwise. But let's delve deeper into the heart of this cosmic schism. The Hubble constant isn't merely a number. It's the cadence of creation, dictating how swiftly space unfurls between every point in existence. When we measure it locally, using Cepheid variables, those pulsating beacons whose brightness waxes and wanes in predictable rhythms, we ladder our way outward, each rung calibrated by their intrinsic glow, cross-checked against supernovae that blaze as standard candles across the void. These yield the higher value around 73, painting a universe that's hurtling apart with vigor, as if propelled by an unseen urgency in the here and now. Contrast that with the cosmic microwave background, the faint whisper of the universe's birth cry. Captured by Planck, this radiation map reveals the density ripples from which all structure sprang. Feeding those into our lambda CDM model, cold dark matter laced with dark energy's repulsive push, we derive a gentler pace, 67. The math is elegant, the fit snug against observations of galaxy clusters and the large-scale web of filaments threading the cosmos. Yet the two refuse to converge. It's as if the universe speaks in dual tongues. One from its cradle, serene and measured, another from its maturity, frantic and unbound. This isn't a mere rounding error, it's a chasm that hints at fractures in the foundation. Early attempts to bridge it invoked measurement flaws. Perhaps dust obscured our Cepheids, inflating distances, or maybe supernovae weren't as uniform as assumed, their detonations varying by environment. Webb, with its crystalline infrared vision, was meant to dispel these ghosts, and in some ways, it has. Recent analyses from 2025, pooling Webb's data on hundreds of Cepheids in distant hosts, refined the local rate to 72.6, with margins tighter than ever. No hidden crowds of stars muddling the signal. No systematic biases lurking in the calibration. The higher value stands firm, but the tension persists, even sharpens. A study from January 2025 proclaimed the universe expanding too fast for physics to explain, with new supernova surveys pushing the discrepancy beyond 5 sigma, the gold standard for discovery. Cosmology, once a symphony, now echoes with dissonance. Enter the voids. Not mere empty spaces, but gargantuan underdensities, bubbles where matter thinned out in the early turmoil. Our Milky Way, it turns out, might nestle in one such expanse, the KBC void, spanning billions of light years. From within, the surrounding denser regions pull outward, mimicking accelerated expansion. It's a relativistic illusion, gravity's subtle bend on a cosmic scale. Sound waves from the Big Bang, baryon acoustic oscillations, leave imprints in the CMB, rings of density that should space galaxies predictably. But 2025 mappings, cross-referenced with Webb's galaxy catalogues, show distortions. Earth in a void. These waves suggest skewing our local Hubble upward by precisely the amount observed. A July paper from EarthSky detailed how these primordial echoes support the idea, potentially dissolving the tension without invoking exotic physics. Yet not all agree. Some 2025 studies, like those from the University of Chicago, argue Webb's refinements align the rates closer to 70, hinting the tension is fading. Their 3-method cross-check, Cepheids, red giants, carbon stars, yields overlap with Planck, suggesting our model holds. No crisis, just evolving precision. This push-pull mirrors the universe's own duality, expansion versus gravity, light against dark. If voids are the culprit, it challenges isotropy, the assumption that the cosmos looks the same everywhere. A cornerstone cracked. Alternatives abound. Evolving dark energy, where lambda isn't constant, but wanes or surges. Primordial black holes seeding early structure. Even modified gravity, tweaking Einstein's equations at vast scales. Take the Coma Cluster's anomaly. In January 2025, Space.com reported it 38 million light-years closer than expected. Its lensing warped by an intervening void. This isn't isolated. The Hubble tension bleeding into our backyard, with nearby clusters like Virgo echoing the skew. Webb's deep fields reveal more such bubbles, their underdensity accelerating local flows. Simulations probe this, feed in voids and the local Hubble spikes. Ignore them, and harmony reigns. But real voids are messier, their edges fractal, influences cascading. A April 2025 Phys.org piece proposed energy densities as a new gauge, measuring void impacts directly. It could resolve the tension by quantifying how underdense regions inflate the constant without breaking the model. Philosophically, this unnerves. If we're in a void, our vantage is biased. The universe's true pace veiled. It echoes Copernicus in reverse, not central, but peripheral in a rarefied pocket. What other illusions lurk? Alien life, perhaps thriving in denser realms where expansion tempers, stars cluster closer, or quantum ties, entanglements spanning voids to mock locality. The emotional weight presses. We gaze outward, seeking unity, only to find fracture. JWST, our eye into abyss, unveils wonders. Nebulae blooming, exoplanets whispering of habitability, yet amplifies the discord. Retention hinges on this tension, the drama of discovery, the awe of uncertainty, each datum a revelation, building to climax. But mysteries compound. If coma heralds voids as key, why no intermediate Hubble values in transitions? Why the spikes so pronounced, defying uniformity? Do time-varying constants, dark energy morphing, fuel this? Models teeter, incomplete. Voids shape reality profoundly, secrets guarded. Pace ourselves. Telescopes reveal infinity's sprawl. Accrete wisdom gradually, lest it overwhelm. The tension decrees balance, except when cosmos breaks it.